In this video, I'll talk about how to evaluate limits analytically as opposed to graphically. First, easiest method is direct substitution. Now, a thing you should memorize is that we can apply direct substitution to all polynomials, rational functions, functions with radicals, trigonometric functions, and sometimes even composition of certain functions. Let us evaluate the following limits if they exist. Write D and E if the limits do not exist. So part A, we have the limit as x approaches 2 of 2x squared minus 4x. First, I'll evaluate this using properties of limits because we'll have to use this method for more complicated examples. So looking at part 3 here, looks like I have the subtraction of two functions. The limit as x approaches 2 of 2x squared minus the limit as x approaches 2 of 4x. Now the next law I'm going to apply is this one that says if I have a scalar multiple, well, I can just take that outside of the limit. So in this case, I have a 2, I have a 4 inside my limit, so we can take them out. 2 times the limit as x approaches 2 of x squared minus 4 times the limit as x approaches 2 of x. Part 6, if we have an exponent, and if that's a positive integer, then we can apply the exponent after we do the limit. As x approaches 2, we're essentially plugging in 2. So now we have 2 times 2 squared minus 4, and x is approaching 2. 8 minus 8 is 0. Now, if you do every problem like this, you'll notice that you end up doing the same work over and over again, splitting up the limit, and we're going to essentially skip to this step. And that's what we call direct substitution. Okay, so in direct substitution, we say, I recognize this is a polynomial, right? So I can apply direct substitution. For all the x's, I'm going to plug in 2. And then you can evaluate your limit. Part B. The limit as x approaches 2 of 2x plus 7 all over x squared plus 4. We can split this up as before, or if we're using a shortcut, we can say, well, this is a rational function. If I plug in 2 in the denominator, is my function defined? And I'm not going to get 0, so it is, which means we can apply direct substitution, and we say, I'm going to plug in 2 for all the x's. And we say the limit is equal to 4 plus 7 over 4 plus 4. Our answer is 11/8. Part C, the limit as x approaches 2 pi of sine of x minus 3x. Let's split up our limit as x approaches 2 pi of sine x minus, I can take out the constant, minus 3 times the limit as x approaches 2 pi of x. We can apply direct substitution for any trigonometric function. So what is sine of 2 pi? If we plug 2 pi in, the answer is 0 minus 3 times, and if we plug 2 pi in for x, answer to the limit is negative 6 pi. Let's try part D. Once again, two functions added together, and I know each one is defined at negative 2 pi, so I can apply direct substitution if I want to apply the shortcut. Okay, so I have cosine of x minus 49x, but I can plug in whenever this is defined. Cosine of negative 2 pi equals 1. 49 times negative 2 is 98 pi. Now in part E, the limit as x approaches negative 2 pi, we might try direct substitution also. Well, cosine is defined everywhere. 49x is defined everywhere. We can only take the square root of positive numbers. So we plug in negative 2 pi, it's around negative 6, plus 3. We're going to get something smaller than negative 3. So we can't really take the square root of that. If just one of these is undefined, it ruins everything. So on the denominator, we would get the square root of negative 2 pi plus 3, and that does not exist, which means the entire limit does not exist. In part F, we have the limit as x approaches negative 2 pi of cosine of x minus 49x all over square root of 3 minus x. We already evaluated the limit on top. If you plug in, we ended up getting 1 plus 98 pi. On the bottom, we get the square root of 3 minus 2 pi. And that's defined which means our limit exists, all over square root of 3 plus 2 pi. Here we have three separate limits in which direct substitution does not work. Now I'll talk about how we deal with a scenario where we get indeterminate form 0 over 0 if we were to substitute. We have a dividing out technique, rationalizing technique, sometimes the limit does not exist, and we have special trigonometric limits we're going to memorize and learn to apply. For the first limit, as x approaches 7 of x squared minus 49 all over x squared minus 4x minus 21, if we applied direct substitution, we would get 7 squared is 49 minus 49 on top over 7 squared, 49 minus 4 times 7 is 28 minus 21. We would get 0 over 0. This is called indeterminate form because the limit may exist and it may not. We need further investigation. In these cases, we're going to apply some algebraic technique or trigonometric identity to simplify our expression until we get something where we can determine whether or not the limit does exist. What you might do here is factor, and this is called the dividing out technique. If it's a rational function, polynomial divided by polynomial, you might factor it into x plus 7 times x minus 7 over x minus 7 times x plus 3. We can simplify this to make the limit as x approaches 7 of x plus 7 over x plus 3, in which case we can apply direct substitution to get 7 plus 7 over 7 plus 3, 14 over 10 equals 7/5, is presumably the answer to our limit. You might ask, how do I know that these limits are in fact the same? They are definitely different functions, so how can we guarantee that the limits are the same? Well, it turns out these functions look exactly the same if we were to graph them, except this one is undefined at x equals 7. This one is defined there. Now let's try the limit as x approaches 3 of x squared minus 9 all over the square root of x plus 6 minus 3. So if we applied substitution, we would get 3 squared is 9 minus 9, and on the bottom we get the square root of 3 plus 6, square root of 9 is 3, and we would get the indeterminate form 0 over 0. So remember, that means the limit may exist or may not. It's indeterminate. So we need to apply either algebra or trigonometry to simplify this. You just need to be familiar with different ways to simplify things. Turns out if we have two terms in the denominator or the numerator, one of them being a square root, multiplied by the conjugate often makes things nicer. We call this the rationalizing technique. So I take x squared minus 9 all over the square root of x plus 6 minus 3, and I would multiply it by x plus 6 plus 3. Now I have to do the same thing at the top because we cannot change our expression. I'm actually not going to multiply it out on the numerator. All over, we essentially get this squared minus that squared. Square root of x plus 6 squared minus 3 squared. Okay, and that simplifies to make x plus 6 minus 9, which simplifies to make x minus 3. Now if we apply the limit as x approaches 3, 0 times 6 over 0, so it's still indeterminate form. We can factor and then use the dividing out technique. Turns out we can factor this into x plus 3 times x minus 3 all over x minus 3. We can use the dividing out technique again. Say the limit as x approaches 3 of this new function. That is equivalent to old function except at a single point. So we know their limits will be the same. Now we can apply the substitution technique, assuming that it exists. 3 plus 3 times the square root of 3 plus 6 plus 3. So our limit is 36. We have the limit as u approaches 0 of tangent of 8u times sine of 16u all over 4u squared. If we apply substitution, tangent of 8u would be tangent of 0 is 0, times sine of 16u, sine of 0 is 0, over 4 times 0 squared. We get indeterminate form again, which means the limit may or may not exist. We need to simplify using algebra or trigonometry. Now, sometimes these are useful, and we need to memorize these limits to evaluate other limits. The reason why we're learning them now is they're useful for the proof of important theorems. So the first one, if we can get this form of sine of x over x, then the limit as x approaches 0 equals 1. The next one, the limit as x approaches 0 of 1 minus cosine x over x equals 0. So we're basically going to try to get one of these two forms, if we can, if not both, and simplify the trigonometric function. I'm going to start by splitting this up into its separate parts. The limit as u approaches 0 of, now tangent is the same thing as sine over cosine. And we have a sine of 16u over 4u squared. I'm just going to put a u here, and I'm going to put the other 4u here. So they multiply to make 4u squared. Now we want to get one of these two forms of the limit, and it looks like we almost have that here. And it looks like if we group the sine of 8u in this u, we would almost have it in the first location also. So let me group that first, sine of 8u over u. And the second factor will stay the same, sine of 16u over u. And what we have left over is a 4 on the denominator and a cosine of 8u. Now you need to double check that all your expressions are exactly equivalent. It looks like I have sine of x over x, but I really have sine of 8u over, what I need is the same exact thing. So how do I make that an 8u without changing the expression? I'm going to multiply by 8 over 8. So you might say that x equals 8u. Then we have sine of x over x. Likewise here, I have a sine of 16u. I need it over 16u. So to manufacture the 16, I'm going to multiply by 16 over 16 because my expression will remain unchanged. Finally, I have the same limit as u approaches 0 of sine of 8u over 8u times sine of 16u over 16u times, and what I have left over now is an 8, a 16, and a 4 cosine 8u on the denominator, times 8 times 16 all over 4 times cosine of 8u. As u goes to 0, 8u also goes to 0, and 16u also goes to 0. So if I apply substitution here, I can apply this first limit and say that this equals 1 times, and I can apply this limit to get 1 times 8 times 16 over 4 times, and cosine of 8 times 0 is also 1. So the answer is 32.